Hello. So I'm in the new activity, chapter 7, act 5. So this is the first activity. This is about noise. Noise can came from multiple sources. A few examples include dust on a camera lens, grains in a photo film. This one is the desire in analog photography and filmmaking. Errors in CCD sensors and storage, errors during transmissions and reception, and errors while scanning the photograph. Very high amount of noise is not desired. This is because high noise reduces the useful and expectful signal, affecting the quality of images. So this is the code. You can see we're using the import numpy as MP, the import cv2, import random, import matplotlib, point pylob as plt. Then we use our image. So this is the location of my image. It's the same one as the first activity. The name is 1. Then we have the output equal to MP zeros, image, shape, MP, and unit 8. P equal to 0.05. Then we have a 4 with a range of image shape 0, 4 with J in range with shape in 1, R equal to random, point random, and then we have the if, elif, and else. So the first if has R bigger to P divided by 2, output I, J equal to 0, elif R bigger than P, output I, J equal to 255, else output I, J equal to image I, J. Then we have the import I'm show output CMap gray, P title salt, paper, and sprinkle, PLT axis off, and PLT show. So I'm gonna run the program so you have a better look of the image. There you go. So now we're in the next activity. This is activity 2 from chapter 7, act 5. So this is about noise again, but we are using the camera to visualize noise in an image. So we are importing the RPI GPO as GPO, import CV2, import nump as MP, and import random. So in the preceding code, the noise density denoted by P is set to 0.05. We are generating random numbers from each pixel, and if it's less than P minus divided by 2, we set the pixel to black. If it's between P divided by 2 and P, then we set a pixel to white. So I'm gonna run the program so you have a better look of what we're doing here. There you go. So as you can see, you have the camera is pointing to my mouse, and we can see the noise in two colors. So we have black and white depending on the pixel. So as you remember, if the pixel is less than P divided by 2, we set the pixel to black, and if it's between P divided by 2 and P, we set the pixel to white. So you can see the noise that looks like a movie or old video footage. So see you in the next one. So now we're in the activity 3 of chapter 7, act 5. So this is about Gaussian noise. We are using import nump as MP, import cv2, import matplotlib, pylob as plt. So this type of noise is named after the mathematic Carl Friedrich Gauss because the values of noise are normally distributed as known as Gaussian distributed. We can simulate this type of noise as the follows. So the first step is to import the image in grayscales. So my image is the same as always. Then we have to use the dimensions of the image, row columns equal to image shape. Then we convert the image to a float number to process the noise. In this case, we use image equal to image as type mp float 32. Then we have these parameters of the Gaussian noise. So the first one is mean equal to 0. Then we have the bar equal to 0.1, and then the sigma that is equal to bar 0.5. Then we generate the noise, Gaussian noise, by using Gauss equal to mp random normal mean sigma row column. Then we add the noise to the image by using the next block of code, that is noise equal to image plus Gauss. And then we have to show the difference of the absolute original image and the image with noise. So we print abs noise minus image, and then we show the image with noise. So I'm gonna run the program. So this is it. As you can see, it's in grayscales, and is the image that we use in the first activity, as you can see. And there's the title that says Gaussian normal distribute noise. So see you in the next one. So we are in this next activity. This is about position noise. So we are in the chapter 7 act 5, and the noise is distributed according to the position curve and is known as position noise. It is also known as shot noise. This phenomenon occurs because the particles natural in terms of light. Let's take a look of an example code where we will introduce the position noise to an image. So this is the code. First of all, we have the imports, same as always. Then we use the charge the image, and this image as the first activity. Then we have the range of the image from 0 to 1. And so we have image equal to image divided by 255. Then we have to obtain the number of the values uniques in the image to the noise of position noise. So we have balls equal to 2 np cell np log 2 len np unique image. Then we have add the position noise to the image. We have noise equal to np random position image plus multiply by two balls divided by float balls. Then we have scale the range from 0 to 255 and convert it to unit 8. We have noise equal to np clip noise multiplied by 255, 0, 255 as type and np unit 8. Then we have shown the image with noise, position noise. So I'm gonna run the program so you have a better look. There you go. This is the image, and as you can see, we add the position noise. It's not a noise that you can detect in an image. Is something that is pretty difficult to see, but it has the effect in the image. So see you in the next one. So we are in the next activity. This is about noise again. This is random normal noise. So we have already seen an example of Gaussian normal noise. So we can also generate random normal noise as the follows. So we're using grayscales to use an image of with color and add the noise. So first we charge the image and we convert it to grayscales. Then we have the convert float for the process, and then we have to obtain the dimensions of the image with rows and columns. Then we have to generate the noise in a random way. Then we apply the noise to the image. Then we use the scale values of the image in a range of 0 to 255. Then we show the image with noise. So I'm gonna run the program. There you go. This is the image. So we first convert it to grayscales and then we add the noise. So as you can see, there is random places in the image with noise. See you in the next one. So now we're in the next activity. This is about 2D convolution with the sign-up process in a module in SCIPY. So in this program, the main idea is to show 3 images. The first one will be the original, the second one it will be the sharpened one, and the third one it will be the blurred one. So we have the 4 same imports. Then we have to charge the image in a grayscales. Then we have to create the kernel for the blur. And then we have to apply the convolution for the image. Then we have to use the kernel for the sharpen. Then we have to apply the convolution. And finally we use the PLT subplot to show the images. So first of all, let's take a look at the mathematical background of convolution. The convolution is the understanding of how the shape of a function is affected by another function. The process of computing it and result the function is known as convolution. We can perform convolution in 1D, 2D, and multidimensional data. Signals are multidimensional entities. So images are type of signal, so we can apply convolution to an image. In this case, we are using an image of 2D, so it's in grayscales. If we want to use 3D, we will need to change the program. So in this case, it's configured to do a 2D convolution. So I'm gonna run the program. So as you can see, we have the three images. The original image is the first one. Then we have the sharpened image that looks more crispy. And finally we have the blurred image that is very difficult to see the image. You can see it's not sharpened, it's the opposite one. So see you in the next one. So now we are heading to the final activity. This is about 2D convolution filtering. So we are using the CV2 filter 2D function, just like the SCIPY signal convolute 2D function. This convolves a kernel with an image and then applying a linear filter to the image. The advantage of the CV2 filter 2D function is that we can apply it to data that has more than 2 dimensions. So in this activity we are using an image with color, so this is a 3D image. And then that's the reason that we can use this filter to add sharp an image and to see the original and the blur one. So we can apply these colored images with this function. This function accepts the image, the input image to a depth and the output image. -1 means that the input and the output have the same depth. And then we have the kernel for the convolution operations as argument. The following code demonstrates the usage of this function. So as you can see, we have the import CV2, the import nop as MP, the import matplotlib as import, pyplot as PLT. Then we have the location of our image. And in this case, it's an image with color. It's a 3D dimension image. Then we have the input CV2 CVT color image, CV2 point color, BGR to RGB. Then we have the output CV2 filter 2D Input -1 MP1s 5050 MP unit 8 divided by 225, I mean. Then we have the PLT subplot to import the image and the titles of each images. And now I'm gonna run the program so you can see the 3D convolution. Mm, there you go. So you can see we have the input and the output. Maybe you can see the output with lower quality, but in my display it shows that the input has better quality than the output. The output looks more with blur, and the input looks like with sharpness, and it looks a little bit more crispy. So see you in the next one.